Continue our discussion of time representations or time domain representations of linear time invariant systems, and last time we talked about discrete time systems. Now we're going to talk about continuous time systems. Again, as just a quick review, we're going to describe the relationship between the input and output signals for a linear time invariant system, which will be useful to predict and analyze these type of systems' behavior once you know the impulse response. So you can find the behavior or output behavior of the linear time invariant system for any arbitrary input once you are given the impulse response of a system. So we're going to, as I said before, we're going to start with the impulse response, and then from there we're going to completely describe the behavior of any linear time invariant systems for any input and arbitrary signal. So once again, we're going to express our input as a weighted time-shifted impulses for any linear time invariant systems. The output must be a weighted sum of time-shifted impulse responses. Just as we did in the discrete time case, it will be also shown also for the case of the continuous time system. So here we have a linear time invariant system described by our impulse response, here denoted this time as h of t, where the impulse response is a function of time. We have a delta t impulse response. This occurs at t equals 0. And we have the corresponding impulse response. Now if I delay my delta function by tau, my impulse response due to that delayed impulse will also be time shifted also correspondingly. And then for any arbitrary input, which we can think of this as an infinite sum of shifted impulses weighted by x sub tau, and we'll show you this in a later slide. However, the output due to this arbitrary input is related by the impulse response and the input shown here. So this is what we call the convolution integral. So here we have a unit impulse into this linear time invariant system in the continuous time case, and let's say our output looks like this. Our output in this case is the impulse response. Now we delay our impulse at our input by tau 1. Therefore, our output should also be delayed by tau 1. So our impulse response is delayed by tau 1 also. And we can see here, using this equation, which is the convolution integral, this is also the same using the commutative property, and substituting for a time shift in here. So wherever there's a t, we substitute t minus tau 1. Substituting our input for an impulse, we receive this expression, but this integral only exists when tau is equal to t minus tau 1. In other words, this expression here, set that equal to 0, because that's only where the integral exists, is where the impulse exists. So when we set tau equal to t minus tau 1, we have this expression here, which is what we have as our delayed impulse response due to this delayed impulse. Then finally, this is delayed with weight doubled. So our output here is still an impulse response that is time shifted by tau 1, but we double the height, which is 4. Now we're going to focus our discussion on the convolution integral. Here we have a linear time invariant system described by an impulse response. We have an input as an impulse, characterizing this system where we put it as an input and we get our corresponding out response given by h sub t, and let's say our h sub t is given by this. we can take any arbitrary input and compose as an infinite sum of impulses right here. Okay, or mathematically this is described as an infinite sum of shifted impulse weighted by x of tau, or the value at each of these locations of these impulses. Okay, so that's our infinite sum. So this is for an arbitrary input that is broken down as an infinite sum of weighted impulses. Now we're going to derive this convolution integral just like what we did with the convolution sum. So here x of t is broken down as an infinite sum of weighted impulses. Characterizing this linear time invariant system is our impulse response. And the output in terms of the input and the impulse response is described by this convolution integral, and we're going to show how that is done. But it's very similar to the one we did with the convolution sum for discrete systems. So here's our input consisting of an infinite sum of weighted impulses, and we're going to operate on that input. Could be some filtering operation. Because of linearity, as before, we can shift this. Instead of the sum, we shift it inside the integral. Okay, so we shift this inside the integral, so where the shifted impulse right here is part of the argument for this operation. But we note that since this is a linear time invariant system, that the output as a result of this impulse is the impulse response, which in this case we can substitute this expression here, h delta t minus tau, for h of t minus tau, and that's our output. So we can think of the output as a weighted sum of time shifted impulse responses weighted by x of tau right here for particular values of tau, integrated from minus infinity to infinity.